In the nature, a system with more energy is less stable. In other words, the lowest energy state corresponds to the most stable state of the system. So, every system tends to attain stability by losing energy. Let's see how the atoms attain the lowest energy and tend to be in a stable state. We know that the nature is associated with innumerable chemical reactions. It is a known fact that an atom is the smallest particle that takes part in a chemical reaction. Hence, most of the elements exist in a combined state in the form of molecules. The few elements which exist independently are noble gases. This is attributed to the stable electronic configuration and the minimum energy they possess. Hence, the atoms of other elements which do not have stable electronic configuration and the minimum energy combine with other atoms of elements to form molecules. Thus, these atoms attain stability by the means of bond formation. The process of bond formation is associated with the lowering of energy of the system. The attractive force which holds various atoms together in a molecule is called a chemical bond. Covalent and Lewis made an attempt to explain the chemical bond formation in terms of electrons. According to them, noble gases are chemically inert because they have stable electronic configuration. The stable electronic configuration is due to the presence of either 8 electrons in the outermost shell, called octet configuration, or 2 electrons in the first shell, called duplate configuration. Hence, they exist independently in atomic state. On the contrary, the remaining elements having less than 8 electrons in the outermost shell are chemically reactive. Hence, they combine with other atoms of elements by means of chemical bonds so as to attain stable octet. So, they do not exist independently but exist in combined states as molecules. Thus, the Covalent-Lewis approach provides an explanation for the requisite of formation of bonds. Later in 1916, Covalent and Lewis developed the electronic theory of valence or theory of chemical bonding to explain the chemical bond formation between the two atoms. According to electronic theory of valence, every atom tries to attain octet in its valence shell by losing or gaining or by sharing of electrons. This is known as the octet rule. Only valence electrons are responsible for the formation of chemical bond. Except valence electrons, the remaining part of the atom, that is the nucleus with the inner shell electrons, is called kernel. Lewis proposed simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. As per Lewis symbols, the number of valence electrons of an element are represented as dots around the symbol. Let's look at the Lewis symbols of the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon as shown. The number of dots around the symbol gives the number of valence electrons. These valence electrons are useful to calculate the group valence of the element. The group valence of an element is equal to number of valence electrons of an element, or 8 minus the number of valence electrons. This is the significance of Lewis symbols. Now, let us look at the formation of ionic bond or electrovalent bond, which was explained by Covalent by considering the following facts. Halogens which are highly electronegative and alkali metals which are highly electropositive are separated by noble gases in the periodic table. Hence, halogens gain an electron, whereas alkali metals lose an electron to form negative and positive ions respectively. The positive ion and the negative ion thus formed attain octet configuration. The two oppositely charged ions approach each other and form an ionic bond or electrovalent bond. The electrostatic forces of attraction that holds the two oppositely charged ions together is known as the electrovalent bond. On the basis of these facts, let's explain the formation of sodium chloride. The electronic configuration of sodium is 2, 8, 1, whereas the electronic configuration of chlorine is 2, 8 and 7. When both sodium and chlorine combine together, sodium loses its one valence electron and forms positive ion, that is, sodium ion, whereas chlorine gains the one electron lost by sodium and forms the negative ion, that is, chloride ion. The sodium ion and the chloride ion attain the octet configuration of neon and argon respectively. These two oppositely charged ions approach each other and form sodium chloride. Due to the strong electrostatic forces of attraction between these oppositely charged ions, an ionic bond is said to be formed. Thus, sodium chloride is formed by the transfer of electrons from sodium to chlorine. The number of unit charges present on the ion is called electrovalence. In sodium chloride, sodium is assigned a positive electrovalence of 1, while chlorine is assigned a negative electrovalence of 1. Similarly, we can explain the formation of potassium chloride, calcium chloride, magnesium oxide, and other ionic compounds. On the basis of Cosell and Lewis approach towards chemical bond, we can explain the factors that affect the formation of ionic bond. The formation of ionic bonds depends upon the following three key factors. First, the ease of formation of a cation. Second, the ease of formation of an anion. And finally, the arrangements of the positive and the negative ions in the ionic solid. Let us understand this by considering the formation of sodium chloride. In the formation of sodium chloride, sodium loses one electron and attains the configuration of its nearest noble gas, neon. The amount of energy required for the ionization of a neutral atom, which is sodium atom in this example, is called ionization enthalpy. It is always endothermic. Similarly, chlorine accepts one electron to attain the configuration of its nearest noble gas, argon. The amount of energy liberated for the gain of electrons by chlorine atom is said to be electron gain enthalpy. It is represented as delta EGH. It is defined as the enthalpy change when a gaseous atom gains an electron. Note that the electron gain enthalpy may be exothermic or endothermic. Thus, sodium forms a positive ion, that is a cation, whereas chlorine forms a negative ion, that is an anion. Due to the strong electrostatic forces of attraction between these oppositely charged ions, they are held together to form sodium chloride. Now let us understand how ionization enthalpy and electron gain enthalpy affect the formation of an ionic bond. The ease of formation of a cation depends on the magnitude of the ionization enthalpy. Lower the ionization enthalpy, easier the removal of electron, and hence greater is the ease of formation of cation. Similarly, the ease of formation of an anion depends on the magnitude of the electron gain enthalpy. More negative is the electron gain enthalpy, greater is the ease of formation of the anion. Hence, we can conclude that lower the ionization enthalpy and higher the negative value of electron gain enthalpy, greater is the ease of formation of an ionic bond. The resultant ionic compound consists of regular and orderly arrangement of oppositely charged ions in three-dimensional region, held by strong electrostatic forces of attraction. This means that each cation is surrounded by a fixed number of anions and each anion is surrounded by a fixed number of cations. In a crystal of sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions as shown here. The difference in the crystal structures of different ionic compounds is attributed to the size of ions, their packing arrangements, and other factors. Finally, a requisite number of oppositely charged ions combine to form a crystal lattice. This process involves the liberation of energy. The higher the amount of the energy released, the greater the stability of the ionic compound. The stability of an ionic compound can be predicted by calculating the total enthalpy change in the process. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive. But still, the crystal structure is stabilized due to the energy released during the formation of the crystal lattice. For example, in the gaseous state, the ionization enthalpy for the formation of Na+ from sodium is plus 495.8 kJ per mole, while the electron gain enthalpy for the formation of a chlorine ion is minus 348.7 kJ per mole. The sum of the two, which is 147.1 kJ per mole, is positive. But this is compensated by the energy released during the formation of the crystal lattice of sodium chloride, which is minus 788 kJ per mole. The overall energy released is the sum of 495.8 minus 348.7 and minus 788, which results in minus 640.9 kJ per mole. Since energy is released in the process, it makes the crystal lattice more stable. Thus, the magnitude of energy released during the formation of crystal lattice, called lattice enthalpy, provides a measure for determination of the stability of the ionic compound. Thus, lattice enthalpy plays a vital role in the formation of ionic compounds. Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of sodium chloride is 788 kJ per mole. This means that the energy required for the separation of 1 mole of solid sodium chloride into 1 mole of gaseous sodium ion and 1 mole of chloride ion is 788 kJ per mole. Langmuir refined the Lewis postulates and introduced the term covalent bond. The bond formed by the mutual sharing of electrons between the combining atoms of the same or of different elements is called a covalent bond. During covalent bond formation, each atom tries to attain octet, that is, 8 electrons in its valence shell, or duplet, 2 electrons in the first shell. The formation of covalent molecules can be understood from the Lewis dot structures. In the Lewis dot structures, the valence electrons of all the bonded atoms of a molecule are represented by dots. The following conditions are to be satisfied for the formation of a covalent bond in a molecule. Each of the bonded atom must contribute equal number of electrons to the shared pair. A bond is said to be formed when an electron pair is shared between the bonded atoms. All the bonded atoms must attain the nearest inert gas configuration as a result of sharing of electrons. Let us understand the formation of chlorine molecule by writing Lewis dot structure. The electronic configuration of a chlorine atom is neon 3s2 3p5. It has 7 electrons in its valence shell. Hence, it needs 1 more electron to attain the nearest inert gas configuration of argon. Therefore, each chlorine atom contributes 1 electron for sharing, and this electron pair is shared mutually by both the chlorine atoms. This shared electron pair joins 2 chlorine atoms together in the chlorine molecule. That is, if 1 electron pair or 2 electrons are shared between 2 bonded atoms, a single bond is said to be formed. Similarly, let us look at Lewis dot structures which depict the formation of covalent bonds in methane and carbon tetrachloride. Now, let us understand the formation of the oxygen molecule by writing the Lewis dot structure. The electronic configuration of oxygen atom is helium 2s2 2p4. It has 6 electrons in its valence shell. Hence, it needs 2 more electrons to attain octet. When 2 oxygen atoms approach each other, each of the oxygen atom contributes 2 electrons for sharing. Both the oxygen atoms mutually share these 2 electron pairs and attain the nearest octet configuration of neon. As the 4 electrons in 2 electron pairs are shared between 2 oxygen atoms, the 2 oxygen atoms are said to combine by a double bond in the oxygen molecule. Similarly, we can show the formation of carbon dioxide, ethylene, C2H4 molecules by Lewis dot structures as shown. Let us understand the formation of nitrogen molecule using Lewis dot structure. The electronic configuration of nitrogen atom is helium 2s2 2p3. It has 5 electrons in its valence shell and needs 3 more electrons to attain octet. When 2 nitrogen atoms approach each other, they mutually share 3 electron pairs and attain the nearest inert gas configuration of neon. As 6 electrons, that is, 3 electron pairs are shared between 2 nitrogen atoms, the 2 nitrogen atoms are said to join by a triple bond. Similarly, we can show the formation of acetylene, C2H2, and carbon monoxide molecule by Lewis dot structures as shown. Let us look at certain other important steps to be adopted while writing the Lewis dot structures for a molecule or an ion. In case a covalent molecule is formed between different atoms, then the atom with the least electronegativity is placed at the center and other atoms will be placed at the terminal positions as shown here for a carbon dioxide molecule. Now, count the number of valence electrons available for bonding. In case of a molecule, count the total number of electrons present in the valence shell of all the bonded atoms. In case of ions, that is anions and cations, for each negative charge, add 1 electron to the total number of valence electrons, and for each positive charge, subtract 1 electron from the total number of valence electrons respectively. While writing a Lewis structure, it is always better to know the symbols for the respective bonded atoms or the combining atoms while you have to guess the skeletal structure of the molecule. This makes the distribution of the electrons between the bonded atoms easier. Among the valence electrons available for bonding, shared pair of electrons forms a single bond between two bonded atoms, and the remaining electron pairs present on the respective bonded atoms are either used for the formation of multiple bonds or remain as lone pairs. Finally, each atom should attain octet in its valence shell, except hydrogen, which attains the stable duplet configuration. Now let's see how to write the Lewis dot structure for carbonate ion by adopting the above-mentioned steps. First, let us calculate the total number of valence electrons in the carbonate ion shown here. The number of valence electrons in carbon is 4, whereas the number of valence electrons in oxygen is 6. As 3 oxygen atoms are present, the number of valence electrons in 3 oxygen atoms is equal to 18. As 2 negative charges are present on the carbonate ion, add 2 to the total number of valence electrons present in carbon and oxygen atoms. The total number of valence electrons here is 22. Hence, the total valence electrons in carbonate ion is 22 plus 2 equal to 24. In the carbonate ion, as carbon is less electronegative, it is placed at the center, whereas 3 oxygen atoms are placed around it at the terminal positions. The skeletal structure of carbonate ion is as shown. Now let us draw a single bond between the central carbon atom and each of the oxygen atoms. This, however, doesn't complete the octet on carbon, if the remaining 2 electrons on this oxygen remain as lone pair. Hence, a double bond between the carbon and the oxygen completes the octet. This results in the following Lewis dot structure. Now let's see how to write the Lewis dot structure for ammonium ion. First, let us calculate the total number of valence electrons. The number of valence electrons in nitrogen is 5, whereas the total number of valence electrons in 4 hydrogen atoms is 4. And as 1 positive charge is present on the ammonium ion, subtract 1 from the total number of valence electrons present in nitrogen and hydrogen respectively. That makes it 9. Hence, in the ammonium ion, the total number of valence electrons is 9 minus 1 equals 8. In the ammonium ion, nitrogen is placed at the center and the 4 hydrogen atoms are placed around it at the terminal positions. The skeletal structure of ammonium ion is as shown. When each hydrogen is bonded to nitrogen by a single bond, nitrogen attains octet and hydrogen attains duplet respectively, resulting in the shown Lewis structure. Let us now discuss about formal charge. In the case of monoatomic ions, the net charge belongs only to that particular atom. For example, chloride ion oxide ion, sodium ion, magnesium ion, etc. In the case of polyatomic ions, the net charge is possessed by the ion as a whole and it does not belong to any particular atom. But we can assign a formal charge on each atom in the polyatomic ion. Formal charge is equal to the total number of valence electrons in the free atom minus total number of non-bonding electrons minus half of the total number of bonding electrons. While counting the electrons on the atom in a molecule, it is assumed that an atom owns 1 electron of each shared pair and 2 electrons of the lone pair. Let's calculate the formal charge on the oxygen atoms in the ozone molecule. In the ozone molecule, 3 oxygen atoms are present. Of these 3, 1 oxygen atom acts as a central atom. This is the Lewis structure of the ozone molecule. Let us number the 3 oxygen atoms as 1, 2, 3 respectively. Let us first calculate the formal charge on the first or central oxygen atom. The formal charge on it is equal to 6 minus 2 minus half multiplied by 6, which is equal to plus 1. The formal charge on the second or doubly bonded oxygen atom is 6 minus 4 minus half multiplied by 4, which is equal to 0. The formal charge on the third or single bonded carbon atom is 6 minus 6 minus half multiplied by 2, which is equal to minus 1. Remember that the formal charges do not show the real charge separation within the molecule. Formal charges are useful to predict the most stable structure among the possible Lewis dot structures of the compound. Now let's move on to limitations of Lewis theory. Though octet rule is simple, it is not applicable to all the molecules. It is mainly applicable to organic compounds and compounds formed by second period elements such as methane and water. Octet rule is not applicable for the molecules containing odd electrons. For example, there are only 7 electrons around nitrogen in nitric oxide. Octet rule is not applicable for the molecules in which the central atom has less than 8 electrons. That is, contracted octet. This is observed in the compounds or molecules in which the central atom in its elemental state possessed less than 4 electrons in its valence shell. For example, lithium in lithium chloride, boron in boron trifluoride and boron trichloride, beryllium in beryllium chloride, aluminium in aluminium chloride don't possess octet. The atoms of the elements that belong to the third period and beyond the third period possess 3d orbitals available for bonding. Hence, most of the compounds formed from them possess more than 8 electrons around their central atoms. This is called expanded octet. Hence, the octet rule is not applicable for the molecules such as phosphorus pentachloride and sulfur hexafluoride, etc. In phosphorus pentachloride, phosphorus, the central atom has 10 electrons in its valence shell. In sulfur hexafluoride, sulfur is the central atom and it has 12 electrons in its valence shell. We know that each atom gets stability due to octet in its valence shell. But some elements like krypton and xenon forms compounds in spite of having octet in the valence shell, such as xenon difluoride, xenon oxydifluoride, krypton difluoride, etc. The octet rule couldn't explain this anomaly. Lewis theory does not explain about the shapes of the molecules. It also does not explain about the relative stability of the molecules as well as the energies of the molecule. Drawing the atomic structures of complex compounds with bonds is difficult. To overcome this, Lewis established an easy way to represent bonds within molecules and ions. He created it as per the shared pair of electrons and the octet rule. In his method, electrons are drawn as dots and the bonding of a pair of electrons is represented by a line. Therefore, it is also known as the electron dot structure. The Lewis structure for an atom is the chemical symbol for the atom, surrounded by as many number of dots as the number of valence electrons in it. For an ion of an element, we first need to draw the chemical symbol for the element surrounded by the number of valence electrons present in the ion. Then, the whole structure is placed within square brackets, with the superscript indicating the charge on the ion. The charge of the ion is the number of electrons gained or lost. To draw the Lewis structure for a molecule, first draw the atoms and join them with lines so that for each atom, the total number of valence electrons becomes 8. To draw the Lewis structure for compounds, first, the unit of the negative or positive charge should be deducted from the total number of valence electrons of the compound. The remaining number of valence electrons should be distributed as the bonding pairs of electrons. For example, a carbonate ion has 2 negatively charged units. The number of valence electrons in a carbonate ion is the sum of valence electrons of 3 oxygen atoms and the valence electrons of the carbon atom. That is 22. Therefore, the number of electrons to be distributed in a carbonate ion will be 22 minus negative 2, that is 24. In the Lewis structure, the least electronegative atom occupies the central position, which is carbon here. Now, when 24 electrons are distributed among 3 oxygen and 1 carbon atoms, it looks like this. After assigning electrons, the remaining electrons are utilized for multiple bonds or remain as lone pairs. We will replace each pair of bonded electrons with a line. Notice that the total number of valence electrons becomes 8 for each atom. With the sharing of valence electrons for the full octet in each atom, the Lewis structure involves the octet rule. However, there are some molecules in nature that do not follow the octet rule. In some molecules, the number of electrons surrounding the central atom is less than 8. For example, beryllium hydride and boron trichloride have 2 and 3 pairs of electrons respectively surrounding the central atom. In molecules with an odd number of electrons, such as nitric oxide, the octet rule is not satisfied. The octet rule also does not apply to the molecules with expanded octets. Though the octet rule is based on the inertness of noble gases, some noble gases, such as xenon and krypton, react with other elements and form compounds. The octet theory also does not explain the shapes of molecules and energies of orbitals. However, the molecules that do not follow the octet rule can still be represented by the Lewis electron dot structure. Therefore, though the Lewis structure involves the octet rule, it is not limited to the octet rule. However, in case of polyatomic molecules, there can be more than one possible Lewis structures for a molecule. To determine the best possible Lewis structure for a molecule, we need to find out the structure with the lowest energy from a number of possible Lewis structures. The lowest energy structure is the structure with the smallest formal charge on the atom. Formal charge is the charge assigned to an atom in a molecule, assuming that electrons are shared equally between atoms in a chemical bond. For the correct Lewis structure, it should be other than 0. The formal charge can be expressed as the difference between the number of electrons present in that atom in its isolated state and the number of electrons assigned to the atom in the Lewis structure. For example, in a phosphine molecule, the number of valence electrons in the phosphorus atom is 5, and the number of lone pairs is 2. There are 6 shared electrons among 3 hydrogen atoms and 1 phosphorus atom. Therefore, the formal charge is 5 minus 2, minus half of 6, which is 3. This gives us the formal charge as 0. The Lewis structure and formal charges are applicable only to the molecules formed by covalent bonding. Let's understand what a covalent bond is. In 1919, with the help of Lewis postulates, Langmuir brought in the term covalent bond to define a bonding pattern where the electrons are not transferred. In covalent bonding, atoms share electrons so that the number of valence electrons in each atom becomes 8. For hydrogen, it is 2. Here, the nuclei of both the atoms keep attracting the shared electrons and do not give away any electron completely, unlike ionic bonding. For example, in a water molecule, one oxygen atom shares valence electrons with 2 hydrogen atoms. In this way, the valence electrons in an oxygen atom will be 8, and thus, oxygen gets the stable status of its nearest noble gas, neon. On the other hand, by sharing 1 electron of oxygen each, the hydrogen atoms will have 2 valence electrons each. It will get the configuration of helium. When 2 atoms share 1 electron pair, they form a single covalent bond. For example, the fluorine molecule. When 2 atoms share more than 1 electron pair, they form multiple bonds. In the ethylene molecule, the 2 carbon atoms share 2 pairs of electrons and a double bond is formed between the 2 atoms. Nitrogen molecules form triple bonds. The factors that affect chemical bonds are known as bond parameters. Some such factors are bond length, bond order, bond angle, and bond enthalpy. Let's look at each of these factors. Bond length is the distance between the nuclei of the atoms that are bonded together. It is directly related to the radius of each atom in the bonded pair. In a covalent bond, the radius of each atom forming the bond is called the covalent radius of the atom. In a molecule containing similar atoms, the size of the atoms is the same. Hence, their radii will be the same. In such cases, the covalent radius is half the internuclear distance between the bonded atoms. Another type of radii between atoms is the van der Waals radius. It was calculated by van der Waals and provides the overall size of an atom, including its non-bounded valence shell. It is given as half the distance between two similar atoms in separate molecules in a solid. Some of the methods used to measure bond lengths are spectroscopy, X-ray diffraction, and electron diffraction. The bond length between carbon atoms in an ethane molecule is calculated to be 1.54 angstrom units. The carbon-to-carbon bond length in ethylene is 1.33 angstrom units, while in acetylene it is 1.20 angstrom units. This difference in bond length leads us to our next parameter, bond order. The number of chemical bonds between a pair of atoms in a molecule is called the bond order of the molecule. Bond orders can be calculated from Lewis structures. For example, in ethane, two carbon atoms share one pair of electrons. Therefore, the bond order is said to be 1. In ethylene, two carbon atoms share two pairs of electrons. Therefore, the bond order is said to be 2. And in acetylene, two carbon atoms share 3 pairs of electrons. Therefore, the bond order is said to be 3. Now, if you observe the bond order and the bond length of these molecules together, you will notice that they are inversely proportional to each other. This is because as the number of shared pairs of electron goes on increasing, the distance between the two nuclei forming the bonds goes on decreasing. From the Lewis dot structure, we get the sequence of atoms in a molecule. But what about its structure? For this, we need to look at the next bond parameter, bond angle. It helps us create a three-dimensional structure of the molecule around the central atom. In a molecule, the angle between the orbitals present around the central atom is called the bond angle. In a methane molecule, there are 1 carbon and 4 hydrogen atoms. The bond angle of methane is 109 degrees and 28 minutes. It means that the angle between any two bonds that are formed between a carbon atom and the hydrogen atoms is 109 degrees and 28 minutes. Usually, when the bond angle is 90 degrees, the shape of the molecule is octahedral. When the bond angle is 180 degrees, the shape of the molecule is linear. Similarly, when the bond angle is 120 degrees, the shape of molecule is trigonal planar. Bond angles are measured using spectroscopic methods. Another bond parameter, bond enthalpy, is defined as the amount of energy required to break one chemical bond between two gaseous atoms in a molecule. It is expressed in kilojoules per mole. For example, the energy required to break the bond between the two atoms of a hydrogen molecule is 435.8 kilojoules per mole. When a molecule is made of more than two atoms, it consists of more than one bond. In such cases, the bond enthalpy for each bond may be different. Hence, the average of all the bond enthalpies is taken as the bond enthalpy of that molecule. Bond enthalpy is inversely proportional to bond length. This means the shorter a bond between two atoms, the more energy it takes to break it. We have already learned how to write the Lewis structures for different molecules and ions. For certain molecules and ions, more than one Lewis structure is possible. For example, consider the following possible Lewis structures for an ozone molecule. These are the two structures possible. In both the structures, one oxygen-oxygen single bond and one oxygen-oxygen double bond is present. These two structures imply that one bond is shorter than the other. The normal bond lengths of oxygen-oxygen single bond and one oxygen-oxygen double bond are 148 picometers and 121 picometers respectively. But experimentally, it is determined that the bond length between any two oxygen atoms in ozone molecule is the same, which is equal to 128 picometers. This implies that the bond length between the oxygen atoms in ozone molecule is intermediate between oxygen-oxygen single bond and oxygen-oxygen double bond. It means that all the bonds in ozone molecule are equivalent. Therefore, neither structure 1 nor structure 2 explains the observed bond length. It is observed that for certain molecules, one Lewis structure cannot explain all the observed parameters such as bond length, bond strength, and so on. Therefore, more than one Lewis structure is required to explain all the observed parameters, as a single Lewis structure is inadequate to represent the molecule accurately. If a molecule that can be represented by two or more structures which differ only in the arrangement of electrons, then the molecule is said to be in resonance, and the set of several possible structures are called resonance structures or canonical structures or canonical forms. Any two resonating structures are represented by inserting a double-headed arrow between them. It is important to note that there is no equilibrium between the canonical forms. All the canonical structures have similar energy and the same arrangement of atomic nuclei, but differ in the arrangement of electrons. However, the molecule never actually has the structure of any of the canonical forms at any point of time. The actual structure of a molecule is a hybrid of all resonance structures possible. It is called a resonance hybrid. This resonance hybrid is more stable than any of the contributing resonating structures. In this example, the resultant of these two structures, that is, the resonance hybrid, explains the equivalent nature of the bonds and the observed bond length, which is 128 picometers as shown here. Let us reinforce this concept by considering the possible Lewis structures of a carbon dioxide molecule and polyatomic nitrate ion respectively. We can represent a carbon dioxide molecule by the three following Lewis structures. None of the single structures explain the observed carbon-to-oxygen bond length, which is 115 picometers. The magnitude of this bond length is found to be intermediate between the bond lengths of a normal carbon-to-oxygen double bond, which is 121 picometers, and carbon-to-oxygen triple bond, which is 110 picometers. Hence, the resonance hybrid of these structures, as shown here, explains the experimentally determined bond length. Similarly, we can represent the nitrate ion by the three following Lewis structures. In each structure, there is one nitrogen-oxygen double bond and two nitrogen-oxygen single bonds. However, experimental studies reveal that all nitrogen and oxygen bonds are found to be equivalent. Hence, the resonance hybrid of these three structures depicts the equivalent nature of nitrogen-oxygen bonds. Therefore, the nitrate ion is best described as a resonance hybrid of the three possible canonical forms as shown here. Thus, we can conclude that resonance stabilizes the molecule as the energy of the resonance hybrid is less than any of the canonical structures. Also, a molecule can have only a single structure, that is, the resonance hybrid of all the canonical forms.